Okay, chapter 31, we're talking about scientific notation. Uh, we can write numbers in a different format, and we're specifically talking about really small numbers or really big numbers. Okay, and since our number system is based on 10, then we're going to write numbers in terms of powers of 10. Okay, and so what we see here is the format for a scientifically notated number. So some examples of some scientific notated numbers could be 2 times 10 to the third power. We could have 3 times 10 to the, let's see, negative 5 power. But we always have this times 10 component. Furthermore, we could have decimal numbers. So we could write 1.75 times 10 to some power. Let's say we could make it large. A really large number would have a positive exponent, say 15. Okay. Example of a really small number. Okay, this is very large. If you had this much money, you would definitely consider yourself to be rich. On the other hand, for instance, let's say we had 9.3 times 10 to the negative 13. Okay, this number is very small. And you can tell right away whether a number is very large or small when the number is written in scientific notation just by looking at the exponent. So a very large number with a negative number for the power of 10, very small, a large number for the power of 10 and it's positive, very large. Okay, now what is not scientific notation? Alright, well, if you read the first few comments of chapter 31, you should have read that A, the number in front of the times 10, is a number that's between 1 and 10, okay, but not including 10. Okay, so we only want, if we have a decimal number for A, then we only want one digit in front of the decimal place. So example of what's not a scientific notation would be 15.1 times 10 to the second. And this could be any exponent. The problem is not the exponent. We could have 15.1 times 10 to the negative 3. The problem is we have 15, which is bigger than 10. Okay. We only want one non-zero digit in front of the decimal point. Alright, another example of a non-scientifically notated number would be 0.2 times 10, let's say to the 6. Again, not really important what we put here for the power of 10. And B, the only catch with the exponent is that we want B to be an integer. Okay, so it can be plus or minus, but we don't have decimal numbers or fractions for this power of 10. Alright, and so this is not scientific notation. We have a 0 in front of our decimal point. We want one non-zero digit in front of the decimal point, if there is a decimal point. Okay, so hopefully that gives you some idea of the type of format that we're going to be talking about in chapter 31. So how do we deal with very large numbers? And on this page, what we do is we start out with some regular numbers. Okay, for instance, 2. All right. And what we're going to do is we're going to take 2 and successively multiply by an additional 10. So in the first case, you could look at this as 10 times, or 2, I'm sorry, times 10 to the 0 power, which is the same thing as saying 2 times 1, which is still just 2. Okay, anything raised to the 0 power is 1. So this is times 10 to the 0. And we could write any singular integer in this fashion, times 10 to the 0. Now, what if we multiply 2 times a 10, and this is 10 to the first power? Well, we simply, what happens is we get 20, and we could look at this as just simply adding a 0 to the back of the 2. Okay. What about 2 times 10 squared? Well, 10 squared is 100, which has 2 zeros. And so, in effect, we take 2 and we add 2 zeros behind it. Okay. And then, what if we multiply by an additional 10? And so, just keep in mind that this is 2 times 3 tens. And so every time we multiply by a 10, we have an additional 0 behind the base number. The 2 is our base number. So 2 times 10 times 10 times 10 is the same thing as 2 times 10 to the third. This format here is scientific notation. And the result is we get 2,000. Okay. And then what if we take this and multiply by an additional 10? And so we now have 4 tens multiplied. We get 2 times 10 to the 4th power. Okay, repeated multiplication of the same number. We can shorten that up by using an exponent. We have 4 tens multiplied. Okay, well this is 2 times 10,000. And note that 10,000 has 4 zeros. And what happens to the 2 is we add those 4 zeros behind the 2 and we end up with 20,000. Okay, now with this number 2, it's all fine and good to talk about adding zeros behind the number, but the way you really should interpret the times 10 to the second or 10 to the third is moving the decimal place. Okay. So with the 2, what we have is a decimal point right behind the 2. And so a more correct way to interpret scientific notation is not adding zeros behind the number. I just wanted to mention that because some of you probably picked up on that. We want to look at scientific notation as moving the decimal place. And so with the 2, and we'll go over here and look at the 20,000. What happened is the decimal place started right there behind the 2. And the power of the 10 tells us to move it 1, 2, 3, 4 places to the right. And so we end up with 20,000. Alright. So how could we write 238 billion in scientific notation? Okay, for it to be in scientific notation, we need a number as our A. Okay, this is the standard format of a scientifically notated number. A is between 1 and 10. We only want one non-zero digit in front of the decimal place, and so what we want to do is put our decimal place right here behind the first non-zero digit. And we also want to write out all of the other non-zero digits along with it. So we just put the decimal point here and we pick up the 3 and the 8 behind it. But in this string of digits, that 8 is the last non-zero digit. And so what we do is we drop off all of these other zeros, and there's 9 zeros here. and we say times 10. What should our exponent be? Well, it's not 9. We don't just count the zeros. Okay, there's 9 zeros here, but that's not the exponent. The exponent is how many places did we move the decimal point. So for 238 billion, the decimal point actually starts here, but we want it over here behind the 2 in order for it to be in scientific notation. To get it there, we had to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. That is what our exponent of our 10 should be. Okay, and an easy way to check your scientific notation to make sure you have the right sign of your exponent is to say, if I have a positive exponent of my 10, then it's going to take this number, my base number, and make it bigger. And 11 definitely makes 2.38 bigger. Okay, it makes it 238 billion. So we go from 2.38 to 238 billion. So to go from a small to a big number in the standard form, we need a positive exponent. Okay, how do we make a number smaller in terms of a 10? Well, what we could do with the 2, since we used the 2 above, and we could really do this with any number. 2's not special. But if we take 2 and we divide it by 10, okay, which is what happens here on this second line, this is the equivalent of taking 2 and dividing by 10. It's just that we've separated the 2 and the 10 into different parts. We wrote it this way: 2 times 1/10. Okay, and as we learned from the previous chapter dealing with negative exponents, we can write 1/10 as a 10 to the negative 1 power. And so here is our scientific notation. Okay, well, what number does this represent? What is this number in scientific notation? Well, 2 times a 1/10, or 2 divided by 10, is a 0.2. Okay, and so what you need to see here is that the decimal place, or the decimal point, started out behind the 2, and we moved it in the opposite direction since it was a negative exponent, and we moved it 1 place to the left. Okay, if this had been a positive 1, then we would move it, okay, this is negative. If it had been positive, then we would move it to the right to get it out of scientific notation. Okay, so what happens when we multiply 2 times 10 to the negative 2? Well, 10 to the negative 2 is the equivalent of 1 over 10 to the positive 2. We can just move the 10 to the denominator, and I didn't make my exponent negative, which I should have. Okay, 2 to the negative 10 is a 1 over 10 squared. Well, what's 10 squared? It's 100. Alright, what's 2 times 1 over 100? Well, that is the equivalent of 2 divided by 100. Okay, and you could put this in your calculator and you would get 0.02. Well, what happened to the decimal point? Well, it started out behind the 2. Okay, we started with a 2 here, and the decimal point was right there behind the 2. And then the effect of the 10 to the negative 2 was to move the decimal place to the left 2 units, or 2 places. So we get 0.02. Alright, so what do we do if we have a 10 times 10 to the negative 3? That's going to move the decimal point left 3 places. From where? Well, from right here behind the 2. Okay, this base number tells us where the decimal point starts, and then the times 10 to the whatever exponent tells us which way to move it and how many places. And so we take the 2 and we move it 1, 2, 3 to the left, and we get 0.002. Okay, and then 2 times 10 to the negative 4, we start with a 2, which has a decimal point there. The times 10 to the negative 4, the negative tells us to move it left, and then the 4 tells us we want to go 4 places to the left. And so here is where our decimal point is going to be in the end, and all of these blanks we fill with zeros, and so we get 0.0002. It's the equivalent of dividing 2 by 10,000. Alright, so how can we write 0.00000000238? Okay, I'm not even really sure which place the 8 falls into. It's a really small number. Alright, but according to scientific notation, we only want one non-zero digit in front of the decimal point. So when we start from the left of the number and we go to the right, the first non-zero digit we run into, first non-zero digit is the 2. And so we want the decimal point to go right behind the 2. So this is our base, 2.38. Okay. How many places did we have to move it to get it there? Well, it started here, and so we had to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 places to the left. Okay, and so our integer power is going to be -9. So in the end, we would write this very small number is 2.38 times 10 to the -9. Okay, and what did I say about the power of 10 in scientific notation? If it's negative, it takes the base number and it makes it smaller, and 0.0000238 is a very small number. So that's one way to check the sign of your exponent. Negative exponents make the base number smaller, positive exponents make the base number larger. Okay, and the workbook has worked out another example for us. They took 7.39 10 to the -4 and they went backwards. Okay, they put it into standard form, the form without the times 10 out to the right. And so this negative exponent makes 7.39 smaller, and you do that by moving the decimal place to the left. If we were to move the decimal place to the right, we would make this number bigger. That's the wrong direction. Negative exponent says we go 1, 2, 3, 4 to the left, and so standard form of this number would be 0.000739. Alright, so example 1, we're going to do a little bit of both. We're going to go forwards and backwards. Alright, so here's a standard notation of a number, and we want the decimal point to go behind the first non-zero digit, so we write 4 times 10, and then we have to figure out the exponent. How far did we have to move it to get it behind the 4? Well, we moved it 1, 2, 3, 4, 5 places. So this would be a 4 times 10 to the 5th. The 5 is positive. It makes the 4 of 400,000, which is bigger. Positive exponent makes the base number bigger. For 0.0052, the first non-zero digit's the 5, and so we want the decimal point to go behind the 5. And in scientific notation, we would write 5.2 times 10. And the decimal point was originally here, and we had to move it 1, 2, 3 places to the right. And so the 10 is definitely going to have a power of 3. But what should the sign be? Well, what sign for the exponent makes a 5.2 smaller? Okay, 0.0052 is smaller than 5.2. A negative exponent makes 5.2 smaller. Okay, so I always, when I want to check my exponent, I orient myself in the scientific notation, and I say negative makes base number smaller, positive makes base number larger, as in the example A. Alright, here's a number that looks like it's in scientific notation, but it's not. Okay, if you look at the decimal point, there are 2 digits, non-zero digits, to the left. Okay, we only want 1. So we want the decimal point to go right there behind the 3. So we write 3.14. Alright, to get that decimal point there, we have to move it 1 place to the left, and so we say times 10 to the 1. Okay, and we're sort of ignoring this times 10 to the negative 3 for the time being. Ignore this part. We want to fix the 31.4. So to do that, we have to take 3.14 and multiply it times 10. Alright, positive makes 3.14 a 31.4, which is bigger. Positive makes the base number bigger. Now that we fixed this base number, we'll tack on the times 10 to the negative 3 behind it. And this still isn't scientific notation because we have 2 tens. We only want 1. What do you do when you're multiplying 2 exponential expressions with the same base? You add the exponent. So we say 1 plus a negative 3. And this becomes 3.14 times 10 to the negative 2. Alright, part B wants us to take a scientific notated number and write it in standard form. Alright, I'm going to put an X here. Hopefully you don't get that confused where the original decimal point is. This is our start, or maybe I should, I don't know, maybe I should use an arrow or something. That's where we start, okay? This is our base number, 7.35. We have a power of 10 that's positive. Positive 9. Positive exponent makes the base larger. To make 7.35 larger just by simply moving the decimal point, we have to move it to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I went too far. I should have just stopped at 9. I got carried away. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and each of these blanks will contain a 0 now. And our decimal point will end right there. So let's write this out with all of the arrows and the loops. 735 with 1, 2, 3, 4, 5, 6, 7 zeros, and now our decimal point's there. Well, what is the word name of this number? We start separating zeros in groups of 3, and so we get 7,350,000,000 with the decimal point right there. So positive exponent 9 made 7.35 larger, and 7 billion is definitely larger than 7.35. Alright, well, next scientifically notated number is 9.987 times 10 to the negative 2. A negative exponent makes the base number smaller, and so to make it smaller by simply moving the decimal, we have to move it to the left. So it's going to start here and move 1, 2 to the left, and any blanks we fill in with a 0, and so we could write 0.09987. And if you like the way it looks, you could put a 0 in front of the decimal point, but it's not exactly necessary. Okay, the next couple pages simply tell you about a function of your calculator. If you go to mode in your calculator, alright, you can change the format of the number that gets output. So if you type in a really big number, let's first look at the mode. Here's the mode button right there. Okay, and at the top you can see normal, scientific, and engineering. And for this class we only use either normal or scientific. It's in normal mode. Okay, it's flashing. I hit enter, and so if I go back to my home screen, second quit, your calculator, a lot of times if you type in a really large number, even though it's in normal mode, it will put it automatically in scientific notation. Okay, even though it's in normal mode. So your calculator can definitely handle scientific notation. Now if we type in a smaller number, say 2,380, then it'll return the normal notation, which makes sense because we do have, when we click mode, our calculator is in normal mode, so you would expect that, 2,380. Okay, what if we want to make our calculator return 2,380 in scientific notation? Well, what we do is we simply go back to, we go back to mode, we arrow to the right to where the cursor is blinking over the SCI for scientific, and we hit enter. That changes the mode of our calculator, and now if we type in 2,380 and hit enter, it'll return it in scientific notation. Okay, and you definitely notice a difference in the notation in that there is no times 10. Okay, the E, the capital E, takes the place of the times 10, and so 2.38 E3 simply means that we have a 2.38 times 10 to the power of 3. Okay, you could say that the E means exponent, or exponent of the 10. Okay, this is scientific notation as well as this E notation, 2.38 E3. Alright, And if you find it easier to enter scientifically notated numbers with an E instead of a times 10, then you can use the E button just the same as the calculator does. The E button is located above the comma here. You can see in blue letters capital E, a double E. Select that, and 3, okay, and it returns the same thing, 2.38 E3. Alright, if we type in 2.38 and then we want to use multiplication instead, times 10 and then an exponent of 3, and we hit enter, it gives us, it still returns this notation, the E, 2.38 E3. Okay, these are the same notations. Okay, now knowing what we know about exponents, okay, the product rule, the quotient rule, this is going to make it easier for us to multiply and divide scientifically notated numbers. I don't want you to take the number, if it's scientifically notated, and convert it back to standard notation just to simply carry out the multiplication or division. Okay, we can use the product and the quotient rule. And these rules also apply to 10, and that's what they're showing us over here to the right. 10 to the m times 10 to the n. We do what we do for any other base. We simply, if the bases are the same, 10, 10, we just simply add the exponents. And if we're dividing the tens, we subtract the exponents. Alright, they've worked out a few examples below. In one instance, we have two scientifically notated numbers multiplied. And what they do is they take the base number, 3.1 from the first number and 2.2 from the second one, and they multiply those together. And then they take the tens with the different exponents and they group those together. Okay? And then they apply the product rule, which gives us 10 to the negative 2 plus negative 4, we get a negative 6. And then 3.1 times 2.2 just gives us the new base number, 6.82. Okay, and this is in scientific notation, so we didn't have to convert back to standard at all to handle multiplication with the scientific notation. We only have one digit in front of the decimal point. We're good. Okay, what about division? Well, we take the base numbers, 9.28 and 5.8, divide those, and we get a 1.6. And then separately, we take the tens with the different exponents, and we divide them. And now we apply the quotient rule, which says we subtract their exponents in order to reduce this to 110. So we say negative 9 on the top. We want the 10 in the numerator, so we keep the negative 9 and we move the negative 7 to the top by subtracting it. Negative 9 minus a minus 7 is a negative 2. And so once again, we divided two scientific numbers without converting back to the standard notation. Okay, example 2, that's exactly what we're going to do. We're not going to convert it to standard notation. We're going to write 2.3 times 7.4, and we're actually going to run into a problem that the examples above didn't run into, but still, we can handle this. we group the tens together. Alright, we multiply the base numbers. I'm going to use my calculator so I can do this a little quicker. And we get 1.702 E1, which means that what we're dealing with here is a 1.702 times 10 to the first power. And it gave us that because we have our calculator set in scientific notation. Alright, so this is what the first set of parentheses works out to be. We can combine these two tens using the product rule, -5 plus 8. We get 1.702 times 10 to the 1, then times 10 to the 3. And now we have two tens, another two tens that we need to combine. And so in the end we write 1.702 times 10 to the 1 plus 3, which is 10 to the 4th power. Alright, so I want you to know how to do this without using the calculator. Okay, because using the calculator a lot of times can slow you down. But when you first start out, if you're unsure of whether you're doing something right or not, just be aware that you can check your answer with the calculator. Okay, I'm going to take the calculator and I'm going to type in these scientific notated numbers. 2.3, I'm going to use the E notation, which means that I don't write the times 10, I just put the exponent -5 immediately after the E. And then close the parentheses and I open a new set and I type 7.4 E for times 10 and then just the exponent, and I don't write the 8 as a superscript, and I hit enter, and it gives us what our answer should be in scientific notation. 1.702 times 10 to the 4. E4 means times 10 to the 4. It's the same thing. Okay. If you don't like the E, you can write it with the times 10 times 10, and then you have to hit the exponent button and write the -5, and then we write 7.4 times 10 to the 8th power, arrow over to get out of the exponent, and then close your parentheses, enter. Same thing. So either way you want to go, whatever's comfortable for you, use the times 10 or use the E. It makes no difference. And so finally we divide. We split this up into the base numbers. We divide those separately, and then we can write our powers of 10 in another fraction. We want the 10 on the level of the base number, whatever that works out to be. So we keep the 10 to the 4 and we move the -7 to the top by subtracting it from the 4. So minus a -7 for the quotient rule between the two tens. And then I'll pull up my calculator to figure out what 9.867 divided by 1.43 is going to work out to be. 9.867 divided by 1.43, enter. We get 6.9 E0, which means basically 6.9 times 10 to the 0, which is the equivalent of just a 6.9. Okay, 10 to the 0 is a 1, and so 1 times 6.9 is 6.9. Now, what is 10 to the 4 minus 7? That would be a 10 to the 11th power, and then we put the traditional multiplication symbol between the 10 and the 6.9, and we're done. This is scientific notation. Okay, let us go back and double check this with the calculator. We have, and I'll put parentheses around the top and the bottom of the fraction, 9.867 E4 divided by 1.43 E. Just the exponent follows the E, and so we have a negative 7 on the bottom. Enter. We get the same thing that we calculated over to the right. 6.9 E is the times 10. It tells us what our exponent of the 10 is. 11. Our base number matches and our exponent matches. So we were right. Well, that wraps up chapter 31. As always, get plenty of practice on Alex. If you have any questions, come by my office. Thanks for watching.